Hi everyone, in this video I'm going over the solution to problem number 3 from the 2014 AP Physics C Electricity and Magnetism AP exam. So this problem has a scientist describing an electrically neutral atom with a model consisting of a positively charged nucleus and a negatively charged electron cloud with a charge distribution given by this row of R function right here, where alpha and beta are positive constants, and this is a function of R, where little r is the distance from the center of the atom. So part A is saying that on the axes below, plot essentially the distribution of the charge either from the nucleus or from the electron charge. So from the nucleus, that's very easy. It's all in the very center of the atom. So you start your line going from plus Q and go to the right. For the electron cloud, though, it's going to be a little bit more complicated. So attacking part 1 first, we have this situation. And again, the nucleus is modeled as an infinitely small point charge. So if you were imagining a Gaussian sphere of radius little r, then as soon as that little r is arbitrarily close to 0 but greater than 0, then you have accumulated that plus Q charge. And that keeps going on forever. What about the electron charge? So here is the plot for the electron charge. The idea is that it needs to start at 0, and it needs to be such that by the time you get to r equals alpha, you're at negative Q. Now, why this shape? This shape I gave because of the following mathematical justification. So I actually did a derivation. I integrated the volume charge density that they gave. So in other words, to figure out the amount of charge enclosed as a function of r, I integrated my rho of v and just plugged in the equation. And the reason I did this now was, one, so that I could clearly justify this in case that might help, and two, so that I had a good idea really of how the negative charge distribution was behaving, and three, because I recognize that in the next part I'm going to need to do that anyway. So in any case, doing this integration, you end up getting this result. Plug in the boundary values, and there is your enclosed charge as a function of r for the negative charge distribution. So what do we see here? We see, first of all, that when r is equal to 0, this thing right here is 1, and we have 1 minus 1, which is 0, which is what we expect. 2, we see that we have a negative exponential decay. We have an exponential decay into negative values, which does correspond with what I have right here. And 3, we notice that at r equals alpha, we have e to the minus 1, and based on the scaling of alpha and beta, that would end up potentially giving us negative Q right here, because we're told that outside of r equals alpha, there is no charge distribution, so it ended up being flat. So, how are the points awarded on part A? So going back to part 1 of part A, they gave 1 point for a graph that starts at little q equals plus q up here. And they gave 1 point for the graph being a horizontal line. In part B, they gave 1 point for the graph starting at q equals 0 for r equals 0. They gave 1 point for a concave upward graph, recognizing the significance of that decaying exponential. And they gave 1 point for a graph that approaches little q equals negative big Q at r equals alpha, and equals negative big Q beyond that point. If you just stopped your graph right here, you probably would not, actually you certainly would not have gotten that point, because after all, the axis does go onward. Now, what about for part B? Part B, they're giving a dashed curve representing the electric field as a function of r for just the positive nucleus of the atom without any electrons. So what they're asking us to do is sketch the electric field as a function of r for the neutral atom as defined by the scientist's model, which includes the nucleus and the negative electrons surrounding it. So just thinking back to Gauss's law, we have that the closed integral of E vector dot dA vector is the enclosed charge over epsilon naught. Now, if we get arbitrarily close to the nucleus, the electric field is going to become arbitrarily large. So that's the point of this vertical asymptote right here as R approaches 0. And also, once we get to R equals alpha, the total enclosed charge is 0. We're done. And after that, the electric field, the enclosed charges remain 0. So just working out Gauss's law, we recognize that we're going to have an E coming out of here times a 4 pi r squared. But long story short, that still means that once we get to R equals alpha, the E is going to be 0 because the enclosed charge is 0. In terms of the other behavior, we're dealing with a 1 over r squared combined with a decaying exponential here. So that's going to bring us to 0 real fast. And again, don't forget to continue your line equals 0 for r greater than alpha. How are the points distributed here? 1 point was given for a graph that is decreasing and between the dashed curve and the x-axis. Another point was given for a graph that goes to 0 at r equals alpha and is 0 beyond that point. So, important thing there. To make sure the grader understands that you've done that, either give very dark shading to your graph on this axis or put an arrow there so that they see that, yeah, you recognize that there actually is a graph there. Now, what about for part C? Use Gauss's law to derive an expression for the electric field strength due to the neutral atom for the following positions at r greater than that actually should say r greater than alpha, not r greater than a, and that should say r less than alpha and r less than a. So here is going to be, again, my little trick with this. Fix it! And as you can see, it is now magically fixed. So for our solution at r greater than alpha, which again I need to fix right here, so again we have our trick, fix it! So we're going to use Gauss's law, and noting that the left side here is just going to be an E times 4 pi r squared because we're talking about a Gaussian sphere of radius r. And note that that enclosed charge is something that we already calculated back when we were doing part A. So we have the left side, E times 4 pi r squared, and then just plug in the value for our enclosed charge, though don't forget to add in the plus q from the positive contribution from that positively charged nucleus. If you forgot to do that, that would be real bad. So in any case, divide both sides by 4 pi r squared to get E of r, and then we get our result here. So next, for r greater than alpha, we simply had 0. So I forgot to mention that. Yeah, for r greater than alpha, we had E equals 0. For r less than alpha, this is our result. So then, part D, based on the model proposed by the scientist, what is the physical meaning of the constant alpha? Well, since we have finished enclosing all of our charge to get 0 net charge by the time we get to r equals alpha, that means that alpha represents the radius of the atom. So I should also note that that other constant beta, which they didn't really ask us anything about, that's actually just a proportionality constant. We noted that back in our graph. That would be the proportionality constant that would be required in order to make the enclosed value of the negative charge simply negative capital Q at r equals alpha. So with the parts of this problem, for the rest of the parts, that is, they gave 1 point for stating and using Gauss's law, which is what we have right here. Note that you do need the dot product here. It's not just an E times dA, it is a dot product of E vector dot dA vector. And they gave 1 point for indicating that the enclosed charge is 0, and 1 point for correctly stating that the electric field is 0. So I would say that by saying this equals that is a direct implication that obviously Q must be 0 because epsilon naught is certainly not 0. It's 8.854 times 10 to the minus 12 coulombs squared per Newton meter squared. Now with part 2, they gave 1 point for indicating the need to integrate with respect to volume to find the negative charge enclosed. So we did that back in part A. They gave 1 point for a correct expression for negative charge as a function of distance r. So if you screwed up the integration. That's okay, you just lost 1 point. They gave 1 point for indicating the plus Q present right here when substituting for the enclosed charge, and they gave 1 point for correct substitution for the surface area of a sphere, that 4 pi r squared. They actually did not give a point for the final answer. Part D, they gave 1 point for correctly stating or implying that alpha is the radius of the atom or the radius of the electron cloud. Now, where did people screw up here? So, according to the official reader, or the chief reader, the intent of the question, this question dealt with Gauss's law. It was not at all like a standard problem with an insulating or conducting sphere. Instead, the students were told that they had a nucleus with a positive charge surrounded by a negative charge distributed non-uniformly. Students had to sketch graphs of positive and negative charge and electric field as a function of r. Then they were told to use Gauss's law to solve for the electric field outside and inside the boundary of this charge at r equals alpha. So, a lot of classes I've heard don't get a whole lot into variable charge distributions when dealing with Gauss's law, but I think that practicing with variable, or that is non-constant charge distributions, is very important, so that because once you have done that practice and you've practiced a number of problems with a non-constant rho, that really helps to solidify your understanding of Gauss's law. And apparently the AP people agree as well, because they gave this problem. Now, what did students perform on this question? The mean score was 4.99 out of 15 possible points, so not very high on this. What were common student errors or omissions? Students could not quantitatively reproduce the correct trend on the graph, qualitatively reproduce the correct trend on the graph. Students did not show each step of the derivation, that is the substitution for Gauss's law. The most common missed step was stating that the charge enclosed was 0. And students did not recognize the need to integrate with respect to volume to calculate charge enclosed by the Gaussian surface. Now, going back on that trend, I would say that a very easy way that students could have misunderstood that problem was going back to part A, with particularly these two parts. A lot of people, I believe, misunderstood what they were actually asking, even though they underlined it. It can still be a little bit easy to make a graph of something that they're not asking for, simply because you're not used to making this type of graph. You're often used to just kind of combining things together in your minds and making a graph like that. But this was not what they were looking for right here. They were asking you just to graph these particular separate things. In other words, this is a problem that you would not have been really able to look up in a textbook very easily. Now, another set of points that students often screwed up. Students used the area of a circle or the volume of a sphere instead of the area of the Gaussian surface when they were plugging in on these integrals. For example, people might have plugged in a 4/3 pi r cubed dr prime, or that sort of thing, and that would have been wrong, because the idea is that the amount of little bitty volume at the edge of a Gaussian sphere of radius little r is going to be given by the surface area of that sphere times its thickness. Well, that surface area is 4 pi r prime squared, and the thickness is dr prime, where again I did a variable change so that I'm not having my integration bounds being the same as my integration variable. Now, that's something important to keep in mind. In other words, figuring out what your volume element is, to figure out how much charge is in, to figure out what your dq is. Well, dq is equal to the amount of little bitty charge in a shell, a spherical shell at a radius of r prime. Well, the volume of a spherical shell is 4 pi r squared dr, and the density being rho, well, you got to multiply that by the volume to get the amount of little dq in that spherical shell. That's important to keep in mind. Another point students forgot to include plus q when calculating the total charge enclosed, back in part C. and students had difficulty explaining the physical meaning of alpha. That's something where you just kind of have to sit back and think about, what is this problem saying, and how does this relate to something that I've had some experience with before, or something that I know about from either physics or back from chemistry class. Now, according to the chief reader, based on your experience of student responses, what message would you like to send to teachers to help them improve future performance? 1. This problem required that students think outside the box. They had studied Gauss's law, but never had to apply it like this. And teachers should look for ways to challenge their students to apply the theoretical concepts they teach in real-world situations. And 2, problems involving non-uniform charge density are not common, but should be a part of the instruction in the Physics C E&M class. So, things to keep in mind. If you have any other questions, please leave them in the comment section, and thank you for watching.